Hey guys, today we're going to talk about patterns of computation. So we're going to be looking at how certain operations can be combined together to create just about any sort of computation that you could want to do. And doing this will allow us to take a certain approach about how we think about developing algorithms. So, trying to come up with patterns of computation is all about generalizing our computation. We've already seen one aspect of generality of computation through polymorphism. So, remember that polymorphism allows us to take functions and make them vary over many different types. So, take for instance these functions that we often use over lists. This is very useful. So, like the length function and the plus plus function that puts lists together, and take and so on, all of these functions, they work over lists of some type, and we don't want to redefine them for every single different type. So we generalize them and we say, okay, length takes a list of any type A. So this allows things to operate over any type. Generalizing your code is very important. It's going to make your code much more powerful, and that you're not going to have to rewrite a bunch more code, possibly introduce more bugs. You're going to get more out of the functions that you write on their own, which is a very good thing. And so polymorphism is very useful for this, and we could build on top of this more by kind of generalizing what sort of computation we do into specific fundamental types of computation. So we're going to look at the very common fundamental types of computation we're doing. There are two very important types of computations that come immediately to mind, although these aren't all of them: mapping and folding. So, mapping, you've already been introduced to quite a bit so far. That's when you are basically taking a data structure. For now, it's usually been lists, and you're applying a function to every element inside of that data structure. And folding is similar. You're applying a function to each element in the data structure, but then you're also combining those elements in a certain way. So let's start with a little bit of an overview of the map function. So map is defined in the prelude, and it applies a function to every element of a list. So it takes a function as an argument. Remember, inside of our type signatures, when you have brackets like this around part of the type signature, you know that, oh, this is a function that's actually being given to map. It's a function from A to B. And then it takes a list of A and returns a list of B, because what it's going to do is it's going to go through and it's going to apply this function to every element inside of this list. So for example, we can apply map the function +1 to a list of 1, 3, 5, 7, and we get back the list 2, 4, 6, 8. We could define map a couple of different ways. One way is through list comprehension. So we could specify that the map of a function f over a list x's is going to be the list. We take every x out of x's here, and we apply f to it. Alternatively, we can do it through recursion. So we'll pattern match. So we'll say when we map any function f to the empty list, we just get back the empty list. And then when we map f to a list with at least one thing inside it, at least one x, we apply f to x, and then we use a colon to rebuild the list, and we map f to the rest of the list. Another function I didn't mention, because it's less of a fundamental function given that it can be implemented using map and fold, but is still worth pointing out, is the filter function. So the prelude function filter takes a function that performs as a selector. So it's like a Boolean function. So it takes some A and returns a bool, and it takes a list of A, and what it does is for everything in this list of A that this function returns true for, it keeps, and everything it returns false for, it throws away. So we could use it to filter out elements of the list. So for example, we could say filter even. So even is the function that returns true if the number is even, false otherwise, over say the list of 10, and it'll only return the even numbers from 1 to 10. Filter can be defined using list comprehension as well. Okay, so we could have the list comprehension, and what we do is we use this guard here to say, well, p of x, only keep every x from the list of x's such that p of x, p being the function that's the selector, is true. Alternatively, we can also define it with recursion. So if we're filtering an empty list, we just return the empty list. Otherwise, we're going to use guards here, and we're going to say if p of x, then we keep x and we keep filtering the list. Otherwise, we just continue filtering the list. Another function that can technically be built out of map and fold, but is still worth mentioning as a fundamental function for building computation, is the zip function. So zip is a function that takes two lists, say like a list of A and a list of B, and it pairs them together into a tuple of corresponding pairs. So for example, if you were to zip the list of characters A, B, C with the list of numbers 1, 2, 3, 4, you get the list of tuples of A1, B2, C3. And notice how it'll cut off wherever the shorter list is. So like there is 4 elements in this list, but since there's only 3 elements in this list, it cut off at 3 elements in total. So as an example of what the zip function could be used for, consider we could define a function pairs here, and we could use it to pair a list with the tail of its list. So then this way you would have a list of a bunch of pairs. So if we paired the list of 1, 2, 3, 4, we'd have a list of a bunch of pairs of the first element and the second element, and now the second element and the element after that. So it's like a list of pairs of the element and the element that comes after it. And then we could use this to make a function that it doesn't sort the elements, but it would tell us if a list is sorted. So we could use a little list comprehension here. What we'll do is, if we have a list x's, we'll get all of the pairs of x's, and then for each pair inside that list x, y, we would test is x smaller or equal to y. And if we AND that whole list, so basically this AND will test if the whole list is true, then we know that the list is sorted. And now we finally get to folding functions. So we'll start with fold R. So there's going to be a few different folding functions. We'll start with fold R, which stands for fold right. So we'll get to what the right is about a bit later. So a fold is going to encapsulate sort of this idea that a number of functions can be defined using this sort of pattern of recursion. So a lot of times you define these functions and you're pattern matching over a list. And so you're going to have the two standard cases of empty lists and a list of at least one thing, x's. And what you're going to do is you're going to pull x out, and then you're going to use some operator. So this x here, I'm just using this as a stand-in for some sort of operator, some sort of binary operator, like maybe plus or multiplication or plus plus to put another list together or something like that. And you're going to combine it with the recursion of the rest of the list, okay, calling the function again on the rest of the list. So let's look at some examples of functions that are defined using this pattern. So sum is an example. So sum, the way it's going to work is you're going to move through the list, and so x in this example, so this x operator is going to be plus, and this v, this value that we return at the empty list, is going to be 0. So the idea is we're adding everything together, and then when we get to the empty list, 0 is the obvious choice for v, because anything plus 0 is just that same thing. It's like we're already done. Similarly, for product, okay, this is the same as sum, but it multiplies everything together. So we're gonna use multiplication for x here, and then the v value is going to be 1, okay, because the multiplication of anything times 1, when this becomes 1, is just that same thing. And, which we just used a second ago to see if everything in the list is true, is going to be, this is the double and that we use for and, okay, this double ampersand, okay, that's what we're going to use for x, and then the v value is going to be true, because anything and true is just going to be that anything. So just a thing to note, this v value, there's actually a name for it. This would be called the identity of whatever this operator is, okay? The identity of this operator. So 0 is the identity of plus, and 1 is the identity of multiplication, and true is the identity of and here. So the general thing we're going to be doing here with fold is we're going to give it some binary operator like and or multiplication or plus, and then the identity value for that binary operator. So to see how we would define each of those functions using foldr, we define sum as foldr plus 0. And notice I'm implicitly putting the arguments here. So sum does take a list as an argument. It's sum of x's. It would equal foldr plus 0 x's at the end. But because you just need to tack x's on both the end of the left-hand side and the right-hand side, you can just put it there implicitly because this is going to return a function that still takes a list as an argument. So we can go through and define each of these operators, and I even added another one here, or, which is the same thing as and, but for or. Each of these operators in terms of the binary operator that is going to be combining everything together and its identity value. Now it's a little useful to look at the definition of foldr itself. So foldr, it's a function that takes another function as an argument. So we're giving it this f is always a binary function. So it takes a function that takes an a value and a b value and returns a b value. Okay. Then it takes the identity value v, okay, for this function. That'll be the b here. And then it takes a list of a. So what it's doing is it's going to recurse through. So this is a binary function f. So what you do is you give it the first thing of the list, and then you give it the rest of the fold. Then you continue folding f the x's until you get to the empty list, and then you give it the identity value. So if we run through a little sample evaluation here, the sum of 1, 2, 3 would be foldr plus 0, the list of 1, 2, 3. And then, of course, this list of 1, 2, 3 is just a special way of writing 1, 2, 3, so on, so on, so on. And here's the trick that you could use to think about foldr. Once you put the list in this format, just replace all of these colons with the plus, okay, with whatever the binary operator here is, and then replace the empty list with the 0. Okay, so essentially, if you were to follow through, like we usually do, the steps of evaluation, this is what you would end up with. It would end up just replacing, so you take the list in its special format like this, in its true format with colons and the empty list, and just replace the binary operator, just replace the colon with the binary operator, and the empty list with the identity value. And that's what foldr is going to evaluate to. This is the way you can think about how foldr evaluates things. So let's go over a few more examples just to show you how many different things can be defined with fold. You'll find that a lot of things can be defined with fold, and then you'll find that almost everything can be defined with fold and map together in some form or another. But just to focus on fold for a moment, the length function is another good example. Okay, so the length function, the way we can do things is we'll create our own binary operator using a lambda expression. So what we'll do is the first argument, okay, we'll just ignore it. And the second argument, we just add 1 to it. Okay, so that will be the binary operator that we use for it. And then the identity value we use for this is again 0 because we're essentially still doing a plus here. So this way we can define length using fold. Another good example is reverse. So reverse, we'll define again our own binary operator. So this time we'll take an element of a list and the rest of a list. Okay, and what we'll do is we'll put that element of a list into a singleton list and add the rest of the list to it on the other side. And then because we're doing plus plus now, the identity value we're looking for is the empty list. And this is a good example of why, if you look at the type of foldr isn't just a binary function that takes an a and another a and returns an a. It's a binary function that takes an a and a B and then returns a B. Okay, so if you look at how this binary function works, this is taking some type A, and this is taking another type that's a list type, and then it returns a list type. So far we've been working with only the list data type. So now the question is, can we use the general pattern of computation over other data types? So we can start off with a question of how would we do the same sort of patterns of computation like mapping and folding over tree data types? So let's start off with a standard definition of a binary tree type in Haskell. So there's a binary tree type. Each node has two trees attached to it. It's generalized over any type A, so it has two trees attached to it and a value attached to it until you get to a leaf type. So look at example tree. So if we define an example tree for this type, node, um, node, leaf 5, leaf 6. I'll have a value, let's say 7 here. Leaf 3. So what would this tree? Oh, we need another value here. 7, 8. So what would this tree look like? So this would be the tree. Okay, we would have 8 here, and that would branch. So 8 right here, and this would branch into this node on the left here, which is a node with 7. Has 2 branches here. And then this node has a leaf 5, 6. Okay. And its other node has a leaf 3 here. Okay, so this is an example of a binary tree using this type here. So how can we define, let's start off with bin tree map. How would we define bin tree map? Okay, so bin tree map is going to take a function that takes an A and returns a B. And then it's going to take a bin tree of type A and return a bin tree of type B. Okay, so what it's going to do is it's going to take this function and it's going to apply it to every element inside of this binary tree and return a new binary tree with a type B attached to it. So how would we define this? So bin tree map, there's going to be 2 scenarios here. So we could start off at the base case. So this would be the corresponding like empty list case, but for this tree. So the base case is going to be a leaf X. So if we have a leaf X, it's going to turn into a leaf f of X. All we do is if we have a leaf, all we do is we just apply the function to the element inside of the leaf. Now on the other hand, okay, the other scenario is we have a node with a left tree, a right tree, and a value X. Okay, so what we're going to do is we're going to have to use recursion on the left and right tree to continue applying our map. So we'll call bin tree map ft1. Okay, and then bin tree map ft2. And then finally, when we get to x here, what we want to do is we want to apply our function to the value x. So we'll apply f of x here. So now we've defined mapping. So now we can do the same sort of idea that we did with lists, but with our tree now. We can just map over a tree. Now what about folding? Okay. Folding is going to be a bit tricky. So let's take this one step at a time. Bin tree fold. So what is the type of it going to be? This is always a good way to start. What is the type going to be? So it's going to be a binary function just like before. The first element of type A, the second element of type B, and then it ends up returning a type B. Okay, same as the second element. Then it takes the identity value B. Then it takes the binary tree A and returns a B. Okay. So remember what we want here. We want the same sort of thing that we do with fold. So like we could, so say if we had this example tree here, we want to be able to, let's say, define a function sum tree that would go and just add up all of these elements together. Okay. That means it's going to return some value B. So if the sum function, if we use the sum function here and returns the value B, the whole thing that's going to return is a B here. Okay, so how do we define this? We're going to have our operator. We're going to have our value B. Okay, and let's start at the base case, leaf X. So what do we do in this scenario? Well, this scenario is actually pretty straightforward. What we do is X, op, V. So when we get to the end, when we get to a leaf, all we do is we add it to our identity value. So pretend that op here is the addition, is operation. Then we would just add it to 0. V would be 0, and we would just add it to 0. So that's not too bad. Now, the recursive case, we have V, node, T1, T2, X. This is going to be a little bit trickier. So we're going to do this in parts. So I'm going to have a let here. Okay. And to start off with, what I'm going to do is I'm going to define a V, I'll call this double prime, okay? And what this V double prime is going to do is it's going to call bin tree folds op V on T1, okay? So what I'm going to do is, you can look at it this way. If we have this tree, the first thing I'm going to do is I'm going to do this side, this 7, 5, 6. I'm just going to be like, okay, get the result of this side. And then once I have the result of that side, what I can then do, okay, is I'll define a V prime here, okay, that's going to be X, okay, this 8 value op V, okay. So then what I'm basically doing is I'm taking this top value. So what I do is I say, okay, V prime is going to be the value of adding together all of the left tree here. And then what I'll do is I'll add this left tree here together. So actually, sorry, this should be V double prime. I'll add this left tree here to this big element here, okay? So now I have this V prime. So now what I need to do is I need to do the right tree. So now I need to call this on the right tree. So I need to call bin tree folds op, okay? And I need to call it on the right tree. However, I'm not going to use V here. Instead, what I do is I use V prime here. So now my new identity value, instead of using the identity value to add at the end, I use the value V prime here, which is basically the value of this whole thing besides the right tree summed up. So this whole thing on the left side summed up. Okay. So this is a little bit complicated to wrap your head around. However, this is how you would manually define how a fold works for binary trees. Now, before we finish up for today, I do want to point something out that is a little off topic, for this tutorial's content, but it's just something that's so cool and shows off just how powerful a language Haskell is that I just feel like I have to point it out. So you'll notice that I defined, instead of just defining like map again, okay, I defined this as bin tree map, and instead of just defining fold again, I defined this as bin tree fold. So map and fold are actually part of type classes. So there's like a class functor. For some reason, the map class is called functor, okay, where there's like a map definition and stuff, and there's a class foldable where there's a fold definition. Okay. And so what I could have done is, instead of defining this as like bin tree fold, I could have been like instance foldable bin tree, where, and then I could define how fold R works directly for bin tree. Okay. So I could have written this definition here as just fold R. Okay. Now, instead of doing that, so this is that isn't the cool part. Not quite yet. The cool part is, if I go up to my definition of bin tree, you'll notice sometimes I'm able to write like deriving, and I'm able to get class definitions for free. So I could try this if I put functor and foldable here. Okay, it doesn't work right away. What I actually need to do is, if you look at the error, it even tells you what to do. It says you can't derive an instance of functor. You need derive functor for this. But when it says you need derive functor, what you need to do is you need to go to the top and you need to add what's called a language pragma, which is basically, this is kind of a little thing. It's like, I want to use this extension to Haskell's default functionality. And I'll add this language pragma. And I'll say language derive functor, derive foldable. Okay. And now I'm able to just write deriving functor, deriving foldable. And now if you look, I'm able to load up GHCI. Okay. And I can say fold R plus 0 example tree. And it sums up my example tree. Same with like map. Okay, I could have done the same thing with map, but it has to be, actually has to be fmap plus 1 example tree. Okay, and it goes through and adds 1 to each element in example tree there. Okay, so I actually didn't even have to write these definitions. I could have just been like, yo, Haskell, implement fold and map for me on the data type that I created, and it'll just do it. Because the idea of what it is to fold and map something is a well-refined idea. So the thing is, because it's a well-refined idea, like how a fold and map should work, it just can figure out how to implement it on its own, which is super cool. There's no other programming language I can think of that's able to do something like this. So it's a really neat thing to point out. So today I showed you map and fold and a few other functions that you could use to then build other functions. So these are functions that are kind of foundations of computation, you could think of them as. And we'll see now, actually, throughout the rest of this course, just how useful these functions are for building other functions. Take it easy, guys.